recap. We've got a kind of chalk shortage today, so I think Hugh... okay, it's good. So, it may turn multicoloured at some point. So, at the end of last time, I was just talking about a nice way to picture the possible states, asymptotic states in the theory, which is sort of special to 1 plus 1 dimensions. It's to do with the fact that particles will inevitably have order along the line. So we started off thinking about sort of pure momentum eigenspace. But I said that if you can sort of use this sort of slightly classical imagery, so you can smear wave packets and wave functions a teeny bit to localize their wave packets. Okay? And then you can imagine setting it up in one way such that the fastest particle is on the left and the slowest guy is on the right. Okay? And then if you run the movie of that state backwards in time, nothing will happen. Okay? These particles will propagate like free particles because they never come close to each other. And that's what we would think of as an in state. And an out state is a corresponding thing where nothing happens in its future. Okay? And then the ordering would be exactly the opposite. So the S matrix, basically the key question we want to ask, okay, in states and out states, well, asymptotic completeness is this fancy statement that essentially that spans the whole Hilbert space. Okay? So any state you like is some linear combination of these things. So in particular, a state that looks very simple in the far past, a given in state, can be re-expressed as a combination of out states. But in general, in its far future, that state will be something very complicated. If its two particles coming together very fast, then there'll be amplitudes to produce lots of different states with different numbers of particles in the far future. So although it looks simple in the past, it will look complicated in the future, and vice versa. And the S matrix is a thing that tells you how to map from one to the other, so it tells you that information. So the S matrix tells you how to expand any in state in basis of outs. Okay, so that will tell you what it turns into, which is the basic question you want to answer. Okay? And it's a sort of piece of infrared data. Okay? It tells about what happens when things are infinitely far apart in the past, how they turn into things infinitely far apart in the future. And there are all sorts of fancy techniques for going from knowledge of the S matrix to learn various shorter distance behavior like correlation functions. For that you need to first of all figure out form factors and then develop some expansion of the correlation function. Or finite size effects, where this technique called the TBA that will be discussed, I think, in lectures later in this school will be talked about. Okay? The sort of starting point for all of that stuff is to know first of all the infrared data of the S matrix. Okay? And formally we'd say we start with a two particle in state, then we'd have AI of theta 1, AJ of theta 2 in would be, well, the first thing it could be is some combination of two particle states. So SIJKL of theta 1, theta 2, the rapidities of the guys coming in, and then theta 1 prime, theta 2 primed, AK of theta 1 primed, AL of theta 2 primed. Okay, out, so it's turned into two particles coming out. But of course, depending on the values of theta 1 and theta 2, you might have enough energy in the bank to create a 3-particle state or a 4-particle state or whatever. Okay, so as theta 1 minus theta 2 gets bigger, so the relative rapidity gets more, you've got more energy left to create stuff, and so you might have ... further things, 2-particle states, 4-particle states, and all the rest of it. And for the 2-particle state, remember that all the states are going to be on shelf. So for the 2-particle states, theta 1 and theta 2 prime, there's sort of discrete options for those. Okay? But for the multi-particle states, you might also have a little integral to do. There's some overall possible momenta. But the multi-particle state consistent with overall momentum conservation. So this is quite a complicated thing. Okay? And because all these extra gadgets keep popping up, the analytic structure of this, even this first component, okay, this first little matrix element of the S matrix can be rather complicated, and that was what I was stressing a little bit yesterday. And it's one of the reasons why we were looking for examples of theories where all those higher ... terms would vanish, because they might give us a hope of finding the S matrix exactly, which is kind of the point of integrability. Okay, so sort of pictorially we draw that first component as AI of theta 1, AJ of theta 2, then AL of theta 2 primed, and AK of theta 1 primed. Okay? And we'll see later in more detail that integrability and existence of higher conservation laws means that we can rule out these dot 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 terms, okay, just as we saw in perturbation theory before. Okay? And in fact, it will also tell us that theta 1 prime should be equal to theta 1, and theta 2 prime should be equal to theta 2, because the masses of the particles will have to stay the same as well. Okay, so these bits would be production amplitudes of the sort that we tried to kill off earlier on. Good. Okay, and I mentioned also briefly last time, there's a handy notation for that, which works neatly in 1 plus 1 dimension, but not in higher, which is that rather than bother right in and out, we'll just order our little symbols, these A's, capital A's, in a way that reflects their order along the line in this wave packet picture. Okay, so notation, which I guess was a Zamolodchikov invention. So we'll let the symbols, let the A symbols live outside these kets, okay, with order on the page reflecting as in, okay, so not reflecting as in reflecting, but you know what I mean, reflecting order in space. Okay, so an in-state goes to a sort of symbol which would be A1 of theta 1, A2 of theta 2, and so on, with theta 1 bigger than theta 2. And out, you can guess for yourselves, it's going to be let's say B1 of theta 1, AB2 of theta 2, with theta 1 now less than theta 2. And so the S matrix just tells you how to swap these symbols round. Okay, so the S matrix tells how to swap or exchange symbols. So you can imagine them as some sort of fancy non-commutative little algebra, sort of quadratic algebra of symbols with these sort of relations. So AI of theta 1, AJ of theta 2 is SIJKL, theta 1, theta 2, theta 1 prime, theta 2 primed, AL of theta 2 primed, AK of theta 1 primed plus, where theta 1 bigger than theta 2 on this side, and theta 2 prime less than theta 1 prime on this side. Okay. And again, we always just use this notation in situations where this plus dot 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 is vanishing, so we're kind of almost assuming that. That's true for the integrable cases. If you try to set up such a notation for a non-integrable setup, then you'd imagine that the exchange of these two symbols would generate further terms depending on these values here. Okay, so integrability will imply, so A, that dot 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 bits, okay, dot 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 here, absent, and B, in fact, theta 1 prime is equal to theta 1, and theta 2 prime is equal to theta 2. Okay? So we'll kind of be working with that sort of idea at the back of our minds, but I'll show you a little bit why that should be true in a minute. Okay, and some other notes is that by Lorentz invariance, which is true of the theories I'm dealing with, and may not be true of theories you come across later in the week, that implies that SIJKL is a function of theta, let's call it 1, 2, which is theta 1 minus theta 2 alone. Okay, we can boost theta 1. A boost corresponds to just a shift of all the thetas, if you figure out what it means. Okay, so that means that theta 1 plus theta 2 gets changed by boosts, while theta 1 minus theta 2 doesn't get changed. So it can only be a function of theta 1 minus theta 2. And then 2.2 is kind of the same as saying that these A's don't commute. Okay? And a fancy way of talking about it is you sometimes talk about them forming a Zamolodchikov-Fadeev algebra. But the sort of fancy algebra language doesn't matter too much, but actually it is quite a useful way of doing calculations, so we'll see later that to actually figure out the implications of things like Yang-Baxter equations and so on, shuffling these symbols around using this idea of this little algebra actually works rather well. It's rather effective. Okay, so that set up the S matrix, and now I should talk about why we know those dot 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 bits vanish and how that's useful. And the argument we're going to use is conservation laws. And then the question comes, how many conservation laws do we need? And that was what was answered a long time ago by Park. It's the same Park as actually is in the Park-Taylor amplitude formula, if you know about that. So conserved quantities. Any questions so far, by the way? There's a danger that I will start to sort of rush and write less and less clearly and speak faster and faster because I'm aware of the sort of finiteness of my remaining time. So you should stop me because I don't really mind how far I get. Okay, so conservation laws. So the key idea, well, sort of V1 of the idea is going to be that the left-hand side and the right-hand side have to have the same value for any conservation laws. Okay, so all the states you might produce later, that the conservation laws have to take the same value as they took before. So the first example of that is overall momentum conservation, we've talked about a lot. But further constraints might further restrict what can come on the right-hand side. In particular, might kill off the dot 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 bits. So the first and simple-minded thing to think is just, well, if you've got infinitely many conservation laws, there are infinitely many things to be satisfied, and a trivial way of satisfying it is just if the particle content and rapidity is on the right exactly the same as on the left. And it might just be too hard to find any other solutions to those, and therefore that will kill off the dot dot dots, okay? And that would kind of imply we probably need infinitely many conservation laws to get all that to work. But it turns out there's a slightly more sophisticated version which can run on just about one extra conserved object. And that's what Park spoke about, and that's what I'll tell you about a little bit before lunch, I hope. Anyway, what do conserved quantities look like from this point of view? They're going to be operators which act on these states. And the simplest example we can think of would be momentum. So momentum would be a pair of operators, let's say P and P bar in the light cone. So we'll say momentum as being spin 1. Okay. But actually in 1 plus 1 dimensions we can kind of split into a sort of spin plus 1 and spin minus 1 instead of P and P bar. Okay, and this will act on a one particle state as, so P on AA theta, its job is to give the left light cone momentum as its eigenvalue, and P bar on AA of theta will spit out the right component, so MA e to the minus theta. If you have a multi-particle state, then obviously it should just act additively. We'll talk about that a bit more in a second. Okay, so what about higher ranked objects? So here's one of the special deals with 1 plus 1, is that we can have higher rank conserved quantities without making the whole theory trivial. Okay, so in general, a higher rank conserved quantity would be something with more tensor indices. Okay, so this one at the moment has got 1 index. With more indices, it's like more copies of either P or P bar. So we'd expect spin S, okay, it's in this kind of simple, to be like S copies of P, okay, momentum. So you'd expect some gadget like QS on AA of theta. Okay? And that would be, just by its Lorentz transformation properties, that if it's like P copies of, so S copies of P, it should be e to the S theta AA theta. Okay, that's something which transforms under Lorentz transformations like S copies of P, but of course it's got a little constant out the front, which is just a scalar, encoding what its actual value is on these different operators. Okay, well, it's hardly when the thing isn't moving at all. So that would be that. But then you can see we can also get, so we could take S or minus S, and we get something like S copies of P bar. So we, in general, we'd have Q, let's call it mod S, would be like S copies of T, and Q minus mod S would be like S copies of P bar. Okay, but both are rank mod S objects. Okay, but this is a particular simple way of splitting your higher ranks or doing your higher rank objects transforming in higher representations of the Lorentz group in 1 plus 1, just because the Lorentz group is so simple. It's basically just rotations, of course, or shifts of rapidity. So everything is simple. That sort of left-right split is, you know, the same sort of left-right split as you see when you do conformal field theory or whatever. Same sort of thing. Okay, now we're going to suppose, so here is where this idea of locality and so on comes in a teeny bit. We'll suppose that these densities, these conserved quantities, are integrals of local densities. Okay, well, classically, you can construct these things, and this was the thing that, for example, Buller and Dodd were looking for. They were constructing, in fact, precisely things that looked like that transformed in these ways. They switched to light cone coordinates before they looked at their equations, and then they looked at higher rank things which were exactly to try and check whether their classical Lagrangians supported the existence of conservation laws with these transformation properties. Okay, and they wanted to find these things as integrals in space of some local density. Okay, so we'll suppose each QS is the integral of some local density. Okay, and that means that's got the one particular important consequence, which is that via this picture of wave packets, remember the value of the conserved quantity is it's conserved, right? So it doesn't depend on what time you take the measurement. So in particular, on a given multi-particle state, you just wait long enough that the particles either go back to the far past or off to the far future, so that all the particles are nicely separated. Okay? And then if you think about your integral in space to evaluate that conserved charge, first of all it's going to see the wave packet for particle 1, and we know how it acts on that. It just gives you this, and then for particle 2, and then for particle 3, and so it'll be additive on multi-particle states. Okay, so this with the wave packet picture implies that QS is additive on a multi-particle state. Okay, so QS on one of my expanded gadgets, AA1 of theta 1, AAN of theta n, is just going to be QA1 brackets S e to the S theta 1 plus QAN brackets S e to the S theta n. On the same state, okay? So the eigenvalue is just given additively. Okay. Now, okay, I used this word asymptotic completeness before, just a statement that states of this form span the whole Hilbert space. Okay, so once we know how Q acts on all states of that form, we know how Q acts on everything. So that in particular implies that the numbers QSA characterize QS completely. So if you're looking for, so we're going to talk, I hope, this afternoon a little bit about constraints on these numbers QSA. And so, for example, if you could prove that all of these little QS's had to be 0, then you'd have proved that capital QS, the conserved charge, was identically 0 on all states. It was trivial. Okay. Or alternatively, if you calculate them, then you know the action of this thing on all states. Okay. And since they're simultaneously diagonalized by all these asymptotic states, they also all commute. Try not to put the wet rag on the laptop. So they are simultaneously diagonal, therefore all commute. So we're talking about a set of commuting conserved charges. Now, there do also, in more complicated models, when there are these little internal indices, okay, these little labels, which I'm not going to talk about very much, but in more complicated models, even in the sine-Gaussian model, there's an option to have what are called non-local charges as well. Okay, so there may be, there may also be non-local charges. Okay, and they can be very useful because they've got a little bit more teeth in some sense, and they allow you to get more of a handle on, for example, what the S matrix must be. But we'll ignore them for now, because we just want to draw the best consequences we can from ones we're thinking of at the moment. But if you do have a structure of non-local charges, for example, versions of sort of supersymmetric theories in 1 plus 1 dimensions, or sort of souped-up versions of them have a nice little algebra of non-local charges, then they act by sort of shuffling around this little A index when they act on states. Okay, so it might sort of shuffle you from source onto it, or in some more non-local way when it acts on a multi-particle state as well. Okay, but I'm not really going to talk about this. Good. Okay, so implications of the Qs. Okay, so we're going to suppose, so here I'm making a leap, but we're going to suppose that we've somehow decided that our theory does have some of these non-local, so these local conserved charges QS, i.e. QS with mod S bigger than 1. Okay, translation invariant theories will always have some QS with S equals to 1, that's just P and P bar. And they might have some with S equals 0, for example in sine-Gaussian, which has a topological charge, which actually doesn't transform at Lorentz transformation. But we want to assume that we've got some charges with S bigger than 1. You might have heard of something called the Coleman-Mandula theorem, saying that that's actually ruled out in higher dimensions, and I hope we'll see in a moment why that should be, why in higher dimensions the existence of even 1 or 2 of these charges, well, basically one of higher spin, okay, higher S, is enough to render the S matrix trivial, and so the theory is essentially a free theory. But in dimension 1, there's still a little loophole. So what do? Well, they imply 3 nice properties, which are the properties we kind of want to be able to make progress on computing the S matrix. Then I'll give you a little sketch of the argument, which I say is kind of hinted at in an old paper by Shankar and Witten, but really done in most precision and detail in a paper by Park from 1980. Okay, so they imply no particle production, B, equality of initial and final sets of momenta, okay, which is a step up from A, because now we know that things can't If it's, say, a 3-to-3 process, there'd still be freedom, just conserving overall momentum, to redistribute the momentum among three outgoing particles. Well, that doesn't happen. And of course, we saw last time in perturbation theory, the reason for that is these sort of funny delta function from this conflicting I epsilon business. But it turns out that if there's a conservation law, then perturbation theory has to come up with a sort of cunning maneuver to come up with that result, because otherwise it wouldn't be consistent with the conservation laws. And C, so a bonus that we might not have expected yet, is factorization of S n to n, so the particle, the S matrix involving n incoming particles, into a product of 2-to-2 S matrices and the Yang-Baxter, which most people have probably heard of already, but I'll explain the equation constraining S2-to-2. Okay? So once we've got past stages A and B, we still need to calculate the S matrix for all n. Okay? We still don't know what that is. And part C tells us that actually all we need to do is to compute how two particles turn into two particles when they bump into each other, and that's enough to have a very simple formula for what happens when n particles bump into each other. Basically, they just scatter pairwise, and there's no sort of funny business. So in the more general theory, even if you knew the 2-to-2 S matrix, which tells you what happens when two particles hit each other with no one else around, when you look for the 3-to-3 S matrix, if you sort of cook things up so all three particles are hitting each other at the same point, there's a bit more energy available to you, and some new thing might happen which is not visible in the 2-to-2 S matrix. Yeah?
All these conditions, they are independent from each other. And factorize the abilities and one versus.
Obviously the sort of implications kind of work up the blackboard, but down the blackboard, I don't know, you can try and work out. I mean, of course, in the end, the only examples that anyone knows are examples which satisfy all three, so kind of the logic is a little bit hard to disentangle. But sort of, in terms of the strength of the property, the implication is going down, so the weakest one is A, then B, then C. I don't know, maybe there's some pathological example which isn't the Lorentz invariant or something where something funny happens. But I'd slightly doubt it. Okay, so why do these follow? So this I hope I'll get through before lunch. Well, the best argument is Hark. Let's say it's also there's a paper by Shankar and Whitten. The Hark paper, I think it was 1980. Not quite when Shankar and Whitten, well, a bit before maybe. Okay? And the key idea is to try and use these charges to generate sort of transformations on the states. So I'm going to sketch this. You can find the details. Well, oh yeah, by the way, I should say these, and most of what I'm saying, if my notes and my handwriting is illegible, then these notes of mine that are on the web kind of contain a superset of everything I'm saying. And but even there, and I don't really go through too many details of what Park said, but his paper is pretty readable actually. It's quite nice. You can find the reference to it there. So the key idea is to consider the action of, let's just write it slightly figuratively, as e to the I alpha qs on a wave packet a theta. Okay, so we've got a particle travelling along. Okay, its wave function is at a certain place with a certain rapidity at a certain time, and we hit it with e to the I alpha qs. Okay, so with approximate rapidity theta. Okay, so this is kind of like the standard exercise for looking at how wave packets work and all the rest of it, to see how they move around and what the phase delays are and so on when they bump into each other. Okay, so for s equals plus or minus 1, so e to the I alpha p and e to the I alpha p bar shift wave packets, or well, more strictly speaking, their trajectories in space-time in a theta-independent way. Okay, well that's not fun, right? That's momentum. Momentum generates overall translations of everything. So it doesn't matter how fast I'm moving, if I hit myself with something, the transformation generated by momentum, I'm suddenly moving with the same velocity kind of over the other side of the projector. Okay, it doesn't matter how fast I was going here, I get shifted the same amount over here. Okay, that's fine. But for s bigger than 1, so mod s bigger than 1, the shift depends on my rapidity. So I'll move more or less depending on how fast I'm going. It's a quite easy exercise just to check that. Just, write down. It's actually slightly easier if you just look at the spatial component of momentum and convince yourself that way. But just write yourself a standard little wave packet. Okay, so for mod s bigger than 1, the shift depends on theta. Okay, so that's it. It depends on how fast I'm traveling. Yes, please.
Well, if we try to add with this e to the I to b of some state which is created by a, it seems that in our notation nothing will actually happen because they don't know about the particle notation.
That's right. So that's why I said here. So I wrote a of theta, and I said with approximate rapidity theta. Okay, so you always got to think that at this level of the discussion, I've rubbed it out now, but I've always smeared my thetas a little bit, so I'm dealing with distinct wave packets at distinct locations. Okay, and then, as I also mentioned last time, you have to worry a little bit because you know that wave packets secretly do disperse a little bit as time goes by. So you've got to worry that all of these arguments don't break down because the wave packets disperse before the interactions have happened and so on. And Park actually worries about that and goes through it quite carefully and checks that everything is still all right. But it's a good point to worry about. So I'm using a slight. So this is why I said here approximate. So it's going to have some spread of rapidity. Okay, and that will give it some, that's what uncertainty principle business, it'll give it some little spread of position as well. But because you're allowed to wait as long as you like before you look at any of this spreading out, you can have as small an effect as you want. Okay, so there'll be approximately located here, and I can wait long enough that the other one I'm worrying about over here is so far away that they're not talking to each other. Okay, so that's the line of argument. I agree, it's kind of, we're using a slightly, waving my hands around as I speak. It can be made precise. Okay. And it's actually one of the curious things is that in the whole analytic S matrix game, the initial books by people like Elop and so on, they seem to try to get everything from pure properties of analytic functions. Some of the stuff in the 70s on this, they really try to input also locality of the field theory much more directly. So they talk all the time about trajectories of particles and so on, which should be understood in this kind of approximate sense. They developed a whole formalism to make it all very precise. Which of course then makes the papers very unreadable, but the basic idea is just this. Okay. Right, and so we also have, again writing slightly figuratively, that my S matrix, I alpha QS S e to the I. Okay. I can act, right? The conserved charges commute with the S matrix because they're conserved. Okay. So I can take my initial state with some particles charging towards each other. I can act with this operator to move stuff around a bit, then let the moved around things interact, and then undo that shifting around. Okay? And I should get the same answer as I had if I'd left the whole thing alone. So I can rearrange the initial configuration of particles coming towards each other in any way I like, using these e to the I alpha QSs. Okay, so we'll use this to relate any unwanted amplitude to one which must vanish on general grounds in any quantum field theory. Okay, so that's the first step. And then the second step will be we'll show that any amplitude that we can't show as zero must at least be related to an amplitude we can show is simple and has a factorized form. Okay, so that was sort of A. And of course the question is, do we have enough freedom? Can we waggle our wave packets around sufficiently, rearrange them, using the cues that we've got. And that's another thing that Park spent some time checking. Okay, so that was A, and B is relate remaining amplitudes to easily computed quantities. Okay, and so slightly more. So in some sense, if we're in high dimensions, this is precisely where you can see an argument for the Common-Mandula theorem. We have two particles, two wave packets, say, about to collide. Okay, and before they get to each other, we act with one of these cues such that the two wave packets miss each other completely. Okay, they then sail past each other, and then we kind of undo it, and they're now on sort of trajectories going apart from each other, and we've shown that that is trivial. Okay, that scattering is trivial. Okay, and that's a sort of simple-minded argument for why in high dimensions particles with these higher conserved charges must scatter trivially. So the S matrix is trivial, and that's a sort of at least a good way on the way to saying the whole theory is basically just a free theory. Okay, if you suppose that you can reconstruct everything from the S matrix. Okay, but in 1 plus 1 dimension it's a little bit more tricky, because if you've got two particles coming towards each other, if you rearrange their trajectories, they're still always going to cross. So it's a little bit more complicated, and that's in some sense a loophole in the Common-Mandula theorem, which allows non-trivial things to happen. So sketch of A. So say we've got some production amplitude of the sort that I was trying to kill in perturbation theory, like that. Okay? Then some of the outgoing momenta are going to have to be different from some of the incoming momenta. Right, if everything's on shell, it's kind of easy enough to see. So we'll relate that to, so here's some region where particles are close together. My little wave packet picture doesn't really work so well anymore. There's some interaction going on, which I don't really want to worry about. Okay? But at least here, when these two particles are propagating, they're propagating as free particles because their wave packets haven't yet overlapped. Okay? And if I act with these conservation laws, it turns out that I can, as long as they act differently on trajectories attached to different rapidities, I can manage to peel off. So say this is A1 and A2, and B1 to Bn. I can convince you that you can reshuffle things around by acting with this cue in such a way that the trajectory of the particle Bn, when continued backwards in time, okay, so this is now part of the out state. Okay, I've related it to something where Bn has been moved kind of a long way off to the right. Okay, and it would have had to, it will have to come from A2 before A2 knows about A1. Okay, and that violates, well, the fancy way to say it violates a property called macro causality. Okay, when there's always a little bit of a fuzz about these things when we're dealing with wave packets, but we can make these distances as large as we like by just going further back in time. Okay, so this violates, so call this one 1 and this one 2, and 2 must vanish by what's called macro causality. Basically, so causality and locality essentially is what's going on here. There's another way to think about it. This would mean that A2, before it got to know about A1, had suddenly spat out particle Bn. Okay? And if A2 is one of the asymptotic states in the theory, it can't go doing that because then it wouldn't be an asymptotic state anymore. It would sort of always be at risk of turning into a Bn plus some other stuff. Okay, so 1 equals 0 as well. Okay, and you can do this trick basically for any amplitude where the set of out momenta is different from the set of in momenta. Okay, so that gives us A and B, two initial particles. Okay, the only way out of this is if the outgoing momenta are equal to all the incoming momenta. And in fact also, we have to have that these, okay, just from these numbers Q, these little q's, have to be the same for the corresponding particles. So not just the masses have to be equal to the outgoing particles, but also these Q's for the higher S's have to be the same as well. Okay, so this rules out all amplitudes, all, let's say, S matrix elements where the set of out momenta is not equal to set of in momenta. So that implies A and B, at least for two initial particles. We'll talk about more initial particles in just a second. Okay. So now for two initial particles, we know what's going on. So for two initial, we have A1 of theta 1, A2 of theta 2, going into AB2 of theta 2, AB1 of theta 1. I've been a little bit careful here. So B1 not equal to A1 is possible. So long as QS A1 is equal to QS B1 for all S, okay, including S equals 1. Okay. If that's true, then all my manoeuvring to shift these wave packets around before and after the collision will always have exactly the same effect on this guy as on this guy, so they'll always kind of stay lined up in the same way. Okay, so I can't rule out the amplitude like that. So that's already told us quite a lot. Now, what about if I have three particles? Well, the way to argue that is as follows. This will give us the Yang-Baxter equation as well. It's all kind of slightly physicsy argumentation. There we go. Okay, so see where the chalk runs out. Spend so long destroying it. Right. Well, one way to think about this is let's imagine we could just switch off the interactions for a moment. I'm not really going to need to do this, but it'll help me draw the pictures. Okay. So if I switched off all the interactions, then there'd be three possibilities for my three incoming wave packets. There'd be three options. So depending on their relative positions before they hit each other, I could either have this, one, or if I was really unlucky, or really cunning, I could arrange that they hit each other at the same moment, or the second two would hit first, and then the third one would arrive, sorry, the first one would arrive later. Well, if I switch on the interaction again, remember that I'm dealing with a local theory, then in pictures 1 and 3, nothing really changes. Right? Because at the time that, say, particles 1 and 2 hit each other, particle 3 is a long way away. And likewise for the other two collisions. Okay, so we switch on again, and 1 and 3 are essentially unchanged. Right, the space-time picture of what's going is really not any different. There might be a sort of little, but not macroscopic phase delay going on, nothing dramatic. Okay, while 2 intends to be something new. So those are unchanged, let's say, by the 2 to 2 result. Okay, obviously in a general theory, when you switch the interactions on, each of these could now turn into production amplitudes. But we've already decided that when two particles come and interact, they only ever produce 2, given these conservation laws. Okay, but even then, 2 might be new. Okay, because we now seem to have rather more energy available to us at the point of interaction, we might be able to create some new particle. But, same argument as before, using e to the iqs, we can shift the relative disposition of these trajectories around, as long as s is bigger than 1. Okay, so, but, using e to the I alpha qs with mod s bigger than 1, we can show that 1 equals 2 equals 3. Okay. So, in fact, all is unchanged. Okay. And furthermore, well, okay, for 1 and 3, it's clear that the amplitude is just the product of these 3 bits, okay, just some basic quantum mechanics type arguing. Okay. For 1 and 3, S3 to 3 is S2 to 2, S2 to 2, S2 to 2. So that goes to property C, which is factorizability. Okay, so now it's left to you to think about, well, it's kind of obvious, but if I had 4 particles or 5 particles in my initial state, I could do the same thing. Okay, so I can have situations where the 4 or 5 particles or whatever are coming towards each other in a very nice way, such that they only ever touch each other pairwise. And for pairwise interactions, I've got complete control of it from my 2 to 2 situation, and the amplitude is just given by the product of the pairwise amplitudes. Okay? The only trouble comes when they're all bumping into each other at the same time, but we know that doesn't give us anything new because we can re-disentangle it using our e to the iqs. Good. So that's basically what we needed. Okay. Right, other little comments. Well, one of them is that the equality. Well, okay, so I'll maybe just say this in words rather than write it down. But so far, it kind of looks as though we only need 1 extra conserved charge, okay, 1 higher spin thing. Part looked at this quite carefully, and he concluded that actually 2 were, to rule out some exceptional situations where, by some exceptional configuration of momenta, you couldn't disentangle things properly. He sort of convinced himself and convinced people reading the paper that if you've got 2 of these conservation laws, okay, so in fact, part needed QS1 and QS2 with mod S1 larger than 1, mod S2 larger than 1, okay, to make the whole argument completely bomb-proof. But it turns out that, for example, S2 equals minus S1 will do. So if you've got a parity symmetric theory, then it's kind of always you get for free the conserved charge with the opposite value of the spin, just on swapping P and P bar. Okay, so it's not a big problem. Okay, so it's rather cute, because in some ways what you've got here is an idea that at least within a local quantum field theory, just 1 extra higher spin to a Q plus or minus S charge is enough to give you all these miraculous properties and believe you've got a sort of integrable or exactly solvable theory. So you're kind of in a rather odd situation that rather than worrying whether your infinity of conserved charges is big enough, which is something that maybe John Sebastian will worry about later today, I'm not sure. Here, for these situations, actually just proving the existence of 1 extra conservation law is enough. Okay, so rather surprising, and it became very powerful. So it's a bit of an aside, but one of the places where this whole thing became rather popular is in the subject of perturbing conformal field theories, which I mentioned in the first lecture briefly. So there are situations where you take a conformal field theory, which has obviously very, very many conserved charges, and you deform it by adding in some operator. It's a little bit like adding an explicit mass term. Okay, it's something that Sasha Zanologikov discussed. And he had an extremely cunning sort of counting argument, basically looking at the possible anomalies that could arise in conservation law. So if you have conservation law in your conformal field theory, and you ask yourself, once you've deformed it by adding in this extra mass term or whatever, what could go wrong with your conservation laws? What possible operators could you put in on the right-hand side that would violate the conservation law? And he had a sort of counting argument. So in cases of at least super renormalizable theories with strictly relevant perturbations, where you expect the structure of the Hilbert space of the perturbed theory to be basically that of the conformal field theory, he had a neat little counting argument which showed that in some cases, at least for some low-lying higher spin charges, there wasn't anything available in the theory. There wasn't enough stuff in the available theory to contribute those anomalies. So you knew that that conservation law must survive. This argument didn't work for infinitely many spins. Okay? It worked for some low-lying spins. So even if in these perturbed theories you believe that there's an infinity of conserved charges, he was only able to prove for sure that they existed for the first 3, 4, or 5 of them. Okay? But then he could say, but that's enough for me, because via this argument of Park, I know that that's enough to guarantee factorizability of the S matrix, which will then allow me to do my later calculations and sort of make progress on what the spectrum of masses in this theory are and so on. And I might talk a bit about what he did on that later. So it's rather important that it's actually possible to show factorizability of S matrix, all that sort of stuff, on the basis of just a finite number of conservation laws. Of course, if later on somebody comes along and produces a full mathematical solution of the theory, proving the existence of everything, then all those arguments might be a bit outdated. But I think it's quite nice to understand that that's all you need. Okay. Second comment is that the equality, which sort of, in quotes, looks like S times S times S is equal to S times S times S, from 1 being equal to 3 in these two diagrams, is in general non-trivial. Okay? If these little internal labels, if A1 here can be different from B1 here and A2 different from B2 here, then in evaluating this amplitude, it's actually a product. Okay, there's some little free indices going on these inside these internal on-shell lines. Okay, which means that this is a product of free copies of the two-particle S matrix with the indices all tied together in one way. And this is a product of the same 3 S matrices, but the indices are glued together differently. Okay? And that gives you a non-trivial constraint called the Yang-Baxter equation. Okay? And that's basically the same as the compatibility condition RRR equals RRR that was mentioned yesterday. Possibly with a shift of theta to something, but anyway, it's basically the same gadget. Okay? In fact, there's a whole way of, although that was in the context of lattice models, you can kind of think of all of these pictures. There's a very nice paper by Baxter, where he talks about something called Z invariance, where he sort of shows how you can sort of think about these sort of things. So if you have more particles flying around and more intersections, you can kind of imagine you're building up some sort of lattice from the intersection of all these particles flying together, where there's then a sum over all the possible little labels that come inside when you evaluate the whole thing. And that looks like the sort of thing you compute when you're computing a partition function in a statistical mechanical model. It sort of pushes that analogy quite far. But basically it's the same mathematics underneath in both cases. So it's quite nice. Okay? So that's going to be a key tool in the solvability. So now we've got to the situation where we can write down the general S matrix for any number of incoming particles just by knowing what the 2 to 2 S matrix is. And even better, we've got a non-trivial constraint on the 2 to 2 S matrix coming from this Yang-Baxter equation. Okay, and in D bigger than 2, the same argument shows or implies that S is trivial, because we don't just reshuffle these things in such a way that the intersections happen in different orders. We can now go outside the plane of the blackboard and make the particles miss each other entirely. Yeah?
I think that once you impose all these restrictions on the S matrix, you can actually write this instruction for S in terms of repeats.
That's the question.
Well, it's just that I don't remember quite well.
Yes. So if it's a question, the answer is yes. If it's a statement, then the answer is I agree with you. But yes. So the point is, we've now got. Okay. Well, the point is that obviously there are lots of models which are solvable by this way, so there's no unique answer, right? But it gives us a very non-trivial set of constraints. So the general approach that was adopted, certainly initially, this rather famous paper by Zalogikov squared from about 1979, where they go through the ON models. So what you'll generally do is, if you have a situation where this scattering isn't completely diagonal in the sense that you can reshuffle these internal indices, you'll have some sort of symmetry going on in the theory as well. Okay, so you'll input a bit of information about what the overall symmetries of the model are, which will tell you a little bit more about the structure of the S matrix. Okay, so the set of unknowns, your S matrix must respect that symmetry as well. Okay, so that sort of cuts down a little bit the number of unknowns. So you're not in the general question of classifying. So I think John Sebastian even mentioned last time, the general issue of classifying all possible S or R matrices, as far as at least either of us know, is open. Right? But if you require it to have a certain symmetry, then you can boil these equations down, these Yang-Baxter equations, to a set of equations which you can solve up to some scalar factor. Okay? And for the scalar factor, you'll use constraints like unitarity and crossing symmetry as well, and some sort of minimality assumption. So you also input a bit of a physicist's guess of the simplest solution is probably the right solution. And then you'll have a precise answer in terms of some product of gamma functions or rest of it for the different S matrix elements. Okay, so then you'll get an exact answer. Because that's the whole point. If we didn't do that, then we'd kind of be rather disappointed with this whole exercise. Okay. And then you can do cross-checks on those guesses by doing things like recomputing ultraviolet quantities. So here's where this TBA method comes into play, where you can recompute quantities that you knew from other grounds should have certain values in your theory, and check whether your guess gets that right. Okay, that can make you really sure you've got the right answer. Or you could compute correlation functions or something like that, okay, to be really sure. So it's a sort of indirect bootstrapping sort of guesswork sort of way, but it's kind of the same approach as people like Matthias were using for the bigger and more complicated ADS problem of scattering. The same sort of thing. You make a series of, in some sense, educated guesses constrained by the things you know must be true. And if you've got some luck, and your brain is switched on properly, then you'll be able to get to a sort of well-defined formula. Yeah. So I may show briefly the first step. I've got about 3 different things I want to talk about this afternoon, but I'll show a little bit of that story in the next hour, I think. Okay, good. So that I wanted just to mention. It's essentially Coleman-Mandula used some much more fancy business with analyticity and so on to argue for that. But the Shankar-Witten paper, for example, does mention this argument, gives you an understanding of it. Yeah.
I was wondering if we switch on, so we didn't say anything about the particular theory.
Yes.
So if we switch on, presumably in this case, for Mandula theory.
Okay, so there's a get-out. Coleman-Mandula famously has this. So I was assuming an integer S bigger than 1. Okay, so supersymmetry hasn't come down. And obviously, some of these cases, also S for me was always an integer. These cases with non-local charges, actually, as well as this set of integer-valued S's. Okay, you might have an example, for example, with supersymmetry, where there's a spin 3/2 charge in as well. So that's a bonus, you're very happy. And that gives you another way of constraining the S matrix. Because now, you see, if you have just mentioned briefly, if you have one of these non-local charges, then its value before and after the collision here won't necessarily be, it'll sort of involve sort of fiddling around with the S matrix as well. That gives you some constraints on the S matrix, which kind of allow you to find the S matrix by a different manner. But the brute force way is just to go with the Yang-Baxter equation. Okay, and then in some senses, I mean, 1 + 1 dimension supersymmetry is not quite so special. There are all these sort of higher supersymmetries you can use as well, and these all sorts of fancy parafermionic symmetries and all the rest of it. So supersymmetry doesn't have this sort of great special role, I don't think. Okay, how much time do I have? Okay, well if it's over, I think I can. So what I want to do next is talk a little bit about general features of the 2-particle S matrix, which is now the only thing we want to calculate. And then I'll have a little think about what to say for the rest. But I've got about 3 hours more to say, so I'll do some cutting over the lunch break.